Testing, testing, testing. Let's see if it's working. It seems like it. So, this is just a stream to keep myself accountable for going through the psychology content for my MCAT coming up. So, I'm just gonna go through this long ass document today. I have read the whole Kaplan book on psychology, but I want to have like another go through of a lot of content. So I'm gonna try out this Khan Academy like summary. It's 335 pages, but I will probably get through a decent amount of it. Like, let's see, where gonna be a good spot to stop. So like, I'm hoping to get through like 100, 150 pages today, but we will see. I'm gonna stop throughout my time on this document to either highlight or write things down because my MCAT is 10 days away and I'm feeling underprepared for the psych social section because I feel like Kaplan's view of the psychology is too narrow. So that's why I'm using this document. So, I'm going to read everything out loud of me. Maybe you'll like this if you hear me read it out loud. You could just follow along to me as I read. But we're going to try to get through a lot of content. And I will be highlighting if I need to review it, go back and review it. So, let's start off on page 8. Sensory perception. Okay? So there's visual cues. When we look at something, we need to make inferences, which means that when we look at things in our environment, we can have like top down, bottom up thinking where we can draw conclusions, or we can just gather information from the environment and just respond to it immediately. So that's what those inferences are. Some visual cues allow us to perceptually organize. Visual cues allow us to perceptually organize by taking into account the following cues: depth, form, motion, and constancy. So, depth is how far an object is, I believe. So, perceptual organization is these four individual things: depth, form, motion, and constancy. Depth is like, you look at like the depth of that ball. It's basically showing 3D objects and how further away they can be. The form of the object, I'm assuming, is the object's general shape that you see through your visual cues. Obviously, we all know what motion is. It's if we see an object in motion that it will see like a blur because it's going so fast and our eyes can't fully register what the full distinct image is. And constancy is that the object's image won't change over time, that it will always look like that unless something else promotes it to change. Okay. Humans have two eyes which allow them to receive visual cues from their environment by binocular cues. This gives them a sense of depth. So binocular cues is gathering visual cues from the environment. Of course, we do this through our eyes because we can think about it. Our eyes are like binoculars because we have two of them, and binoculars have two of them. And if we think about it, if we use a binocular, we're trying to get depth of an object that's really far away. So, binocular cues looks at depth. Okay. This gives them retinal disparity. Okay. I need to review retinal disparity because that wasn't in my textbook. So retinal disparity is eyes are 2.5 inches apart, which allows humans to get slight different views of objects of world around. Gives human an idea on depth. So retinal disparity is the different pathways that we will talk about later, I assume at least, because we did in my Kaplan book, that it's using the two different peripheral, like the peripheral, what's the word? Like the peripheral visions that we use that are on the opposite sides of the brain. So this is giving us those slightly different views of the world around us. Okay. Convergence. Convergence, let's see what it is. Is it probably, I'm just, before I look at it, I'm probably just going to say convergence is like the converge of the image from those two different views into one. Gives human an idea of depth as well based on how much eyeballs are turned. Gives humans a sense of depth. So basically, what I'm getting from these few terms, binocular cues, retinal disparity, convergence, they're all looking at depth. So, but this one involved with the turning of the head and the eyeballs. So, that makes sense. If you want to see the depth, you have to have the convergence of the image in the eyes. Okay. So things far away tend to have the eyes relaxed. Things close to us, eyes are contracted. So, how should we remember this? Okay. So if eyes are relaxed, so since I'm close-sighted, okay, let's think about it like this. Since I'm close-sighted, my eyes are relaxed for far away objects because I can't see them. But if I want to get it closer to see me, I have to squint my eyes and contracting my eye muscles to see it closer to me. So that makes sense. Why our eyes, when we contract them, help us see things closer, like squinting. Okay. So, humans also have visual cues. Okay. Humans also have visual cues they receive which they do not need two eyes for. These are monocular cues. So monocular cues is just using one eye, while binocular cues is using both eyes for depth. Remember, depth. Okay. This gives humans a sense of form of a object. Okay. So, as I said earlier, form is just the general shape of the image of the thing that we're looking at. Okay. Relative size. So, relative size can infer with one eye, so it's a monocular cue. So, relative size can infer with one eye. The closer an object it is perceived as being bigger, gives this idea of form. So, relative size, so let's think about it. Relative size is the closer an object is perceived as being larger or bigger. So if we have an object closer to us, it's going to be bigger. So if we have, let's just say, we have a Lego piece that's 10 meters away in our living room and we don't see it. But as we're walking, we accidentally step on the fucking Lego piece. Okay? After anger and pain is asserted in our foot, we pick up the piece and we identify that it is a Lego piece because we bring it closer to make it look bigger. And that shows us the idea of its form. Oh my god, it's all connecting. Okay. So, continuing on, interpositioned overlap. Perception that one object is in front of another. So an object that's in front is closer. So let's think of the example of this so it helps me remember it, because this was not in my Kaplan book or in the videos that I at least watched. So interposition is that overlapping of different shapes and objects. So let's think, if we see bars like on windows in a more unsafe environment, let's say it could be a jail, it could be a worser neighborhood for different stores to lock them up at night, we will perceive that those bars will be in front of the window because they're in front of the window, and our perception tells us that it's closer. Okay. So interposition is just looking at and our perception telling us that one object is closer and that it's in front of it. So our relative height. So let's think. So relative size is things that are closer to us is bigger. So relative height is things higher are perceived to be farther away than those that are lower. Okay. So this is similar to size, I'm assuming. So, but opposite. So relative height. Things that are farther away tend to be lower. Things higher are perceived to be farther away than that are lower. Sorry. So, if we see, let's just say, a Chicago building that's a skyscraper, for example, okay? If we see a skyscraper compared to like a 4 or 5 story tall building, we'll definitely think it's farther away because of how high it is, and that's up in the clouds. Okay. So, shading and contour. Okay. Shading and contour uses light and shadows to form depth and craters. So aliens, basically, if they exist, and the craters on the moon. So, shading and contour basically is the idea that using the different gradient of light and its shadows that are formed, we can determine the depth of something. So, if we see shadows in a dark storm and we're outside, since it's summertime, and we see a pool and the shadows basically illuminate the pool, you can see how deep that pool will be. Alright, so shading and contour is using light and shadows to perceive depths. And contour is just if it has a crater looking. Gives it like that crater 3D image. So moniker cues can also give a sense of motion. Right. That makes sense. So if we have one eye closed, we can still see like a swing in motion. If we have two eyes open, we can still see it. But we can still do it with one eye though. So, what is the motion paradox? Let's see. The motion paradox is relative motion. Things farther away move closer, and closer moves faster. That makes sense if you think about it with common sense. So, the motion paradox is thinking about like the idea. So, if we're looking at, let's just give an example. Let's think. So, we have a swing And if we're far away from the swing and we're at a park, we're gonna think the swing's not going that fast, okay? But as we get closer, we can see why let's just say the teenager on it swinging fast and getting ready to jump off. You can tell that it's going much faster than we originally thought at when we were sitting on the park bench far away. So that makes sense, okay? So the motion paradox is the farther away that we are, the slower it looks. And the closer that we are, the faster it looks. So another example could be like a baseball. When you're far away, you'll be like, when you're far away at a baseball game, I guess, for you watching the baseball getting thrown from the pitcher to the catcher, it'll seem that it's not going that fast. And like, why is the batter struggling? But when you're the actual batter and you're closer, it looks much, much faster. So that's two examples of motion paradox. Parallax? Maybe. Not paradox. Parallax. So, this is another term that I never heard, but I heard something in a different terminology. So I had a sort of relative idea about this, but not in this definite definition. Which basically this section is just memorization of vocab words and how to apply them to a reading. Okay, now we're finally to constancy. So constancy is probably the object. That's what I said earlier. I was right. So, I was right about constancy. The perception object doesn't change even if the image cast on the retina is different. So like a ball. The ball of the image doesn't change even when it's farther away. And that's because its size, shape, the color. But if the ball pops, that constantly changes the shape constancy. So, size constancy, one that appears larger because it's closer. We will still think it's the same size. So, relative size is different compared to this because when we bring it closer, it looks bigger. But size constantly, it stays the same no matter what. Got it. So maybe the Lego piece wasn't the best example for relative size. But for that idea that it looks really small, but then you bring it closer, it looks larger. So it could be. But the general size of it, though, is the same. But the image that appears is different. So that's the misconception that I accidentally had earlier. Okay. Shape constancy. A changing shape still maintains the same shape perception. Okay? So, as I was saying, the soccer ball. The soccer ball, when it's popped, has the same shape, but it's just flatter. So, it still has that shape constancy. Okay? So, now looking at. Oh, they have an example for this one. A door opening means the shape is changing, but we still believe the door is a rectangle. Why does the door gotta be a rectangle? You never seen a circular door? I seen one at this one fancy restaurant that I went to a while back, but that's a different topic. Let's stay focused. A color constancy. I'm assuming that an object will have the same color no matter what, even if it's changed in lighting. So let's see. A color constancy, despite changing lighting, which changes the image color following on we understand that the object's the same color. That makes sense. So even though that we perceive that it's a different color, we know it's the same. It's just the different lighting that's affecting that. Got it. Alright. So that's the first section of this perception task. So sensory adaptation. Sensory adaptation is our senses adapting to the change in sensitivity to the stimulus. So that makes sense. Since adaptation is altering your behavior in some way, we can think about sensory adaptation as that we're altering our senses to a change in a stimuli. Okay. So different sensory adaptations. We have hearing, touch, smell, perception, and sight. So hearing's more complex than a couple of these two, but we'll get to them. So hearing adaptation. We have the inner ear muscles, which are located inside the organ of Corti, which we'll be talking about later. But I just remember that off the top of my head right now. It's in the organ of Corti, and they're mechanical receptors that are vibrated through different membranes, basilar membrane and like the tympanic membrane. The tympanic membrane is also known as the eardrum. Okay, so hearing adaptation is basically altering our increased sensitivity to a stimuli for loud noises. So as they have an example on here, it reduces the stimuli's impact on the membrane, the tympanic membrane, and the mechanical receptors in the ear by reducing it over time, the stimuli, by basically, let's think of another term in behavior, habituation, but it's not, it's basically desensitization in this case. Okay, so that's hearing adaptation. So we're altering, our body alters the loud stimulus to prevent damage to the organs. Touch. Touch is just another sense that is desensitized over time. So we can think about this sensory adaptation by the sense that we have our hand on a very hot plate of food. If you hold it there, you're going to be like, ah, that's so hot. Why is it so hot? But over time, your hand's going to be used to it. And you're like, huh, it's not that bad anymore. But that could be also because the plate is cooling down, but it's most likely your touch slash nose receptors are desensitized to that stimulus. Okay. Smell. This is the olfactory bulb desensitization that, just think of example. Let's just say you're doing some volunteer work and you're working by these garbage bins at like a park or something. You're gonna, when you first get there during the day, you're gonna be, that smells awful. But as you work there for a few hours, like picking weeds, cutting the grass around that garbage bin, or just picking up garbage in general, you're gonna be like, it doesn't smell that bad anymore. It's because your olfactory receptors got desensitized to the smell, and it's not sending the same amount of information over time. Proprioception is the sense of where we put our body in space. So I don't really know a good example of this, so let's just look at their example. So goggles that make everything upside down and the perception of the world, eventually you account it over time and flip it back over. Interesting. So like if we're using like drunk goggles, I wonder if that would impact your perception, that your body would adapt to it. But I don't know. It's an interesting case. That's interesting though. I wonder how like that would work though. That your perception would flip it upside down. Like, would you notice it flip? I wonder how long it would take too. Interesting. Alright. So let's just think proprioception. We know that it's the position of our body in space. And that perception adaptation is like if you're upside down, your mind will flip it where it'll be right side up for you after a while. Okay? For sight adaptation, it is the downregulation, upregulation, and light intensity. So we'll talk about this more in that light section. Hopefully, they have the eye section with the depolarization of the optic nerves of the codes and rods. But let's hope we'll talk about this more. So we for downregulation, this is a good way to remember downregulation for sight. We want to reduce the stimulus of sight when it's a very bright light in your eye. One second, I have to excuse me, I was dying. Alright, back to it. So downregulation, we want to use it in the sense that we're in a bright environment. So when we're driving on the road, our eyes want to lower the sensitivity of the light entering our eye so that we can see the road better. So when it's bright out, our pupils constrict, which allow less light into the back of our eye, and it desensitizes both the rods and cones, which makes sense because if we constrict the pupil and reduce the amount of light entering our eye, it will reduce the amount of signal going to the brain to interpret what we're seeing, which may not be the best thing. That's why we should have sunglasses. Upregulation, so this is like when we're in a dark environment. So let's just think we're at the woods or camping somewhere and we forgot our flashlight from our tent or camper, wherever. So we're trying to see and identify different things in our perception. That there's a tree stump there, or there's wood logs for a fire there. So our eyes will upregulate and increase our dark sight regulation, which allows our pupils to dilate to try to increase the amount of light that enters our eye so that we can perceive shapes and different light gradients better. Okay, that makes sense. We're doing pretty good. We're on page 10. Technically, we're on page 12. Not bad. But we're going to keep going. Hopefully, get to like 150 today. How's the time? It's 9:59. We'll take a break at noon. So this is going to be like a 3-hour, 2.5 hour session today until we take a break and then we hit it back. And then I'm going to go through some content with biology and stuff like that later. But let's continue with our psych and soc. That is painful for me to understand because it's so much memorization of vocab. And I like just conceptually understanding things. So that's why I struggle on this section. But it may be different for everyone. So, Weber's Law. Weber's Law is basically looking at that perceptual difference that will be noticed by the individual by different amounts of stimulus applied. So they're using an example that you're using a 2-pound weight versus a 2.0 pound weight, and it feels the same. And you can determine that just noticeable difference threshold is not being reached in this case by doing 2.05 minus 2. Okay? And that'll give you 0.05. And then you divide that by 2. So 1/20th divided by 2. So when you do multiply it, you get 2/20ths basically. If I did that math correctly in my head real quick because I didn't write it out or anything. And then, so that's not a lot. So it'd be like a 0.1 difference. Wow, you can have a noticeably difference when you have a 2.2 pound weight and 2. So when you do that, you'll get 0.2 divided by 2, which you would get like a 0.4 difference, right? Maybe. Or, no, 4, so let's think 4/20ths. Yeah, 4/20ths divided by 2. Multiply it up, you get like 8/20ths. And 8/20ths will equal 0.4. So I was right. Sorry about the non-quick math thinking it out. But basically, it's showing that just notable difference threshold. So that zero point 0.1 threshold, we did not experience it. But when we had a 0.4 threshold difference, we noticed it. So that's what the just notable difference threshold is. That a slight difference in perception, we can notice the difference. Like, we're always getting stimulus in our environment and everything, but we may not notice it all the time. Like, it's hot here, so I have a fan going on. So, I don't notice the fan going on anymore because that hearing Apparently, my microphone died, but that's okay. We'll just keep going on. So, that's fine. It's fine. Everything's fine. We just went through the absolute threshold, the somatosensation, and now we're on the vestibular system. The vestibular system is focusing on balance and spatial orientation. Okay. And it comes from both inner ear and limbs, which makes sense. The inner ear has the different rings in it, called the semicircular canals. And these canals are used for circular rotation. So, when we're on a merry-go-round, we're spinning, and that fluid in those semicircular are also spinning. But they don't stop before we stop spinning, so that's why we still feel like we're moving. This canal is filled with endolymph, and when we rotate, the fluid shifts in the semicircular. So endolymph is basically that fluid that I was talking about spinning in our ear when we're moving. Okay? And the otof organs, which are the uterole and sacral, helps us detect linear acceleration and head positioning. So we'll think about it. Let's think of a way to remember that otolith organs are for linear acceleration. So otolithic organs is, what's a good word that starts with O and it means linear? One slope. How about that? We think about linear with slope, and we can think that Oto means one slope, which in this case will be linear acceleration. Okay. If we go from lying down to standing up, they move. Okay? That makes sense because we're linearly moving. So that we're sitting, and if I stand up from my gaming chair that I'm sitting in right now, we will recognize that we're moving. And now that I'm stressed about that my microphone's not working, I'm going to check it every so often. And it's still working, so we're chilling. Okay. So autolytic organs are looking at the movement of linear acceleration because one slope and linear slope is associated. Okay? And this is stimulated by crystals attached to hairs being moved in the gel. While on the other hand, the semicircular canals have endolymph in them, which is rotating when we circular rotate. So that's detecting that we're moving in a circular rotation. Okay. And as I said earlier, the endolymph doesn't stop, and that's what causes dizziness. Okay. This is just a diagram of that inner ear. Now we have the semicircular canals that are circular, that detect the spinning of that endolymph in the fluid. We have the utercle and sacral, which is for linear acceleration. Cochlea, which is connected to that basal membrane. These organs of Corti, hair cells right here. So, I never really learned. Oh, I have talked about this earlier, the signal detection theory. Wonder why it's down here and not earlier. Okay. So the signal detection theory is looking at the decision on conditions of uncertainty based on a stimuli and unimportant noise. So as I was saying, you're hearing your name in a loud crowd. So that's what this theory is talking about. So I basically talked about it earlier when my mic was probably muted because my headset was being janky. But if it wasn't muted, I can just go through it again. So we'll have hit, false alarms, correct rejection, and miss. I couldn't remember correct rejections earlier, So let's go through it. So let's just think about it in the case that we're in a crowd, okay? And we have our friend calling our name. If we observe that someone is calling our name and we detect that they're calling our name, that would be considered a hit. Okay? If we detect that someone's calling our name but we miss hearing them say it, that would be considered a miss if that signal is present. Alright, let's have another instance. We're in the same crowd and we see our friend and we think we hear them say our name, okay? That would be considered a false alarm because we think they said our name but they actually didn't. They're just chilling in the crowd. Or we're chilling in a crowd. We didn't think we see our friend. We don't think they call our name. And they didn't call our name. That would be called a correct rejection. Note, do not mistake this for type 1 and type 2 errors. Did we even talk about type 1 or type 2 errors? Because I don't really know what that is. Maybe I'll talk about it in a little bit. Okay. So, this is just using different variables to describe this relationship. Okay? So, I don't know whenever we would ever use these on the MCAT, but just to go through it because it's on the document, D comma, or D apostrophe I should say, or D prime, how I would consider it in physics, D prime is equal to the strength of a signal, and C is just the strategy, okay? The D prime equals strength. So if there's a hit, that means there's a strong signal. If it's a miss, then it means there was a weaker signal determined by the individual. That the loudness of the crowd overpowered the signal. Okay. C is strategy. So what are these strategies? I do know this. I have talked about these strategies before and I read about them before. So the conservative strategy is always saying no unless 100% certain that the signal is present. So you're conservatively being no. So you want to say no 100% of the time unless you're fully certain. And this is bad because you might get some misses. Or the liberal strategy. Go liberal arts schools. This makes you want to say yes, even if there's false alarms. Because liberal strategy is, if I associate it to my school, it makes you want to say yes to doing all these extra classes that you may not want to do or you never even thought about doing before. So you have to say yes always, so that should be the liberal strategy. So that makes sense to me. You can find it another way to memorize it. Conservative, you're always saying no unless you're certain. And liberal, you're always saying yes. Okay. So, let's continue into the signal detection theory part 2. Okay. For any signal, have noise distribution. So noise distribution is that loud crowd in the background that could interfere with that signal being perceived that I was talking about earlier. And signal distribution. Signal distribution is looking at how loud that signal is being perceived in that environment. Okay. The difference between the two is D that we talked about earlier, which makes sense because the strength of the signal is equal to the basically that displacement difference, even though it's not displacement, but that difference between the normal signal and that noise subtracted from each other to find that total strength of that signal being heard. And the strategy can be expressed by a choice of threshold, what the individual deems necessary for themselves. So basically, strategy C depends on the personality of the individual and what they want to participate. Okay, if we were to use strategy B, let's say choose this threshold. So anything greater than 2 will say yes, anything 2 says no. So probably hit is shaded yellow and a false alarm is purple. Okay? Not really sure what that really means. But I'm assuming if you put a probability, like if you have over a certain percentage that you think you hear it, then you're going to say yes. If you don't, then it's the no. So that's what I'm interpreting from that. What is a D strategy? So D strategy is using the strength of the signal minus that B strategy. So let's say, so what's this example? So the D strategy is using the example if D prime is 1, so 2 minus 1 is equal to negative 1. Interesting. I don't really understand that, but hopefully it's confusing to me. So I may have to look up an additional video on the different strategies. So let me write that down real quick, because this is actually one of the first things that I'm not feeling too comfortable with, to be honest. Review different strategies for signal detection theory. Let's just say B, D so far. Let's see if C makes sense. Okay. So the C strategy is the ideal observer. Okay. So it minimizes miss and false alarms. So in our strategy, 2 minus equals is anything above 1.5. Anything below is 1.5. It's a no. So when C is 0, participant an ideal observer. If greater than 1, then they're liberal. If less than 1, they're conservative. Okay, what is this beta strategy? I'm getting confused in the statistic analysis of this theory, so I will have to watch a video on this. Let me write down theory C as well. So beta strategy sets a value of a threshold in the ratio of a heightened signal distribution. So that's basically setting a specific threshold for them to determine if they hear it or not for themselves. Okay. We will have to understand this better, and this better, and strategy C a little bit better, and beta strategy. Let me get this so it looks better highlighted. It's my OCD totally that I have. Won't allow me. Alright, this is what I was talking about earlier. Bottom up versus top down processing. So if you think about it, bottom up is using just the environment that we gain from them. So bottom up, let's re-say that, is bottom up processing is using only information that we gather from the environment to determine what's going on. So let's just say we hear a loud bang, and then we see like a deer fall over. We could say that deer got shot. So that's just inductive reasoning, because deductive are using our top-down processing. So we generally perceive things as we never seen them before. We're at top-down processing. We're using background knowledge to influence our perception. So that's like top-down processing, we're thinking about, we can use like a book example. How our teacher always says, use deductive reasoning to fill in what that word is in its context around the words around it in a sentence. So we're using top-down processing to determine what that definition of that word means without actually being told what that word means. And it may not be correct if you're interpreting that sentence wrong. That makes sense. Okay. So let's enter Gestalt's principles. Gestalt's principles are very interesting to me because for a while I just hated them for some reason. But thinking about them, they make more sense to me now. So Gestalt's principles, or Gestalt's laws of grouping, try to explain why we perceive things the way we do. That makes sense. Okay? So we're not going to read this excerpt right here, but let's go into similarities. How about we should read it? Let's just see if it's anything essential. Imagine watching a basketball game on TV. Why don't we tell ourselves that we're looking at a bunch of still pictures, rather influence ourselves as some fluid, realistic representation of the basketball game? That's just an example of like trying to explain why we receive things the way we do. Okay. So it wasn't essential, but it just drives to the point that Gestalt principle is trying to make us understand why we think of things in a certain way. Through this TV example. Like we know it's still images, but we receive it as a real basketball game going on. Alright. So Gestalt's similarity principle is looking at that if items are similar in a group, we're going to group them together. So I think of different circles in a line. As we can see in here. Oh, in this diagram right here. Circles in a line, and then two circles in a line. We'll associate them as a line. Okay? But if we put them squares individually, we're like, that's not correct. There's difference there. So that's basically, we group things based on similar shape and size. Okay. The law of Pregnez, if I said that correctly, hopefully, I don't know. But the law of Pregnez is that we try to map things to the most simplistic and most simplistic perspective, and that's like if you cut it down in half, we will see it like in equal portions. So like I seen a different diagram than this in my textbook that I read, or like my MCAT practice, but we tried to organize them in the simplest form. Proximity is we group things in closer together to each other. So we can group this into like saying this is two lines and then two lines based on their similar shape and how they're arranged. Continuality, this is unique. That if we see different things placed together in a line, they wouldn't be considered in a line, but we can perceive that these, how they're placed, look like they're in a line. So continuality, lines are seen as following a smooth path. That makes sense. Closure is the idea that if we have different shapes, it will form a shape in the middle that's not technically there. So I seen a different example of this where it'd be like, let's see if I can draw on here. Dot, 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 dot. This is not the best. So this is not the best drawing, but even though these dots on here, okay, they're not connected, we can perceive it's like an oval or a circle based on my artistic skills out here, but it's not. So like you can see you think there's triangles here, but it's technically just like V's or Pac-Man looking circles that have a 6 cut out of them. And then symmetry is we see things in symmetry. So like the pregnas. Alright. I haven't talked about the law of common faith, the past experiences, and contextual effects. So let me go through these real quick. Law of common faith. For example, if there's an array of dots and half the dots are moving upwards while the other half are moving downwards, we would perceive the upward moving dots and the downward moving dots as two distinct units. That makes sense. So if we think about, let's think about like Frogger. If we see like the different rows of logs flowing to the right, we'll see it as its own continued fate. But if we see our character keep going up, it's a different fate that it's going through. It's not the best example, but that's the one I just came up with just off the top of my head through this definition that I just read. Law of past experiences. I haven't even named this. That's fine. I'll name it after. It's just gonna be called Psychology MCAT Practice. Actually, let's take a break. So let's just update that. There. So let's continue. Sorry about that. I just had that idea come into my head. I'm just talking over a thing without having a distinct name about it. So, the law of past experiences implies that under some circumstances, visual stimuli are categorized based on our past experience. For example, the English language contains 26 alphabet to form words. If an individual reads an English word they have never seen, they use the law of past experience to interpret the letter L and I as two letters beside each other. Ah, okay. Interesting. I will have to review law of past experiences. But it makes general sense that we're going to use our top-down processing to determine different letters are different from our past experiences. So contextual effects. The context in which stimuli are presented in the process of perceptual organization contributes to how people perceive the stimuli. So, let's see. Contextual effects. The context in which stimuli are present in the process of perceptual organization contributes to how people perceive the stimuli. So basically, if you're based on the context of a certain situation that you're in, you'll perceive information differently. So let's say you're in a context that you're doing a presentation, and you look at your teacher and she's critiquing everything that you're doing wrong, or whatever you're doing right. You're going to notice that she makes different faces at things that you don't properly say correctly, or you may have not have done the best on during your presentation. But if you're just an individual in the crowd watching someone else's presentation, you may not notice her doing these different things. So it's based on the context that you're in. So that's my example of contextual effect. Alright, now we're entering sight. Which sight is very complex. So let's continue. Let's start with the different structures of the eye. Okay? So, as you can see here from this list, it has many different parts that we use in our eye, different organs, and that's why humans' eyes are so complex. And that's why evolution is crazy of how our eyes are formed. So, starting with conjunctiva maybe. Sometimes I just make up my own words, but that's fine. Conjunctiva. It's the thin layer of cells that line the inside of your eyelids from the eye. Interesting. Okay. So if you flip your eyelid inside out, that's where you can see your conjunctiva. Okay. We all know what our cornea is. It's the transparent thick sheet of fibrous tissue at the very front of the eye that light initially enters through. The cornea, I remember this because my grandma told me when I was 2 or 3, I accidentally scratched her cornea, which is no bueno. So that's how I remember this. Cornea is generally associated with scratching the outside of the eye. Okay, so that's what starts the initial bending of light. Anterior chamber. The anterior chamber is space filled with aqueous humor. It provides pressure to maintain the shape of the eyeball to allow nutrients and minerals to supply cells to the cornea and iris. So let's just think of the anterior chamber is associated with aqueous humor, so A and A. Okay? And this is used for the shape of the eye. So that's why your eye is more spherical shape because of this liquid. And we need this liquid to provide nutrients to the cells because every piece in your body has cells and it needs some supply of nutrients to keep replicating and metabolizing different functions to keep it active. Alright, let's continue on with the pupil. The pupil is the opening in the middle of the iris. The size of the pupil depends on if the muscles connected to the pupil are relaxing or contracting. Modulates the amount of light able to enter the eye. So this is what we were talking about earlier. The pupil is contracted or relaxed. So when it's contracted, okay, we want to see things closer up. So it's contracted when we want to see closer up. So that's up regulation, I believe. And we want to have relaxed for looking at far things away. A few points from earlier that we mentioned. The iris is the colored part of the eye. So that's when you say to like a loved one, your eyes are so brown or blue. You're talking about the iris part. And this is just associated with the relaxing or constriction of the eye pupil. So, the lens. If you have taken physics, you have learned a lot about lenses, especially at my school. And we talked about it in the biological perspective of the eye because we had to do two lens practice problems for our homework associated with the eye. So, the lens job of the eye is to bend the light so that it can be focused on the retina, especially the fovea of the retina, which allows us to perceive the light and depolarize the different rods and cones of the eye. So that's the basic job of the lens, to focus the light and bend it to reach the retina. Alright? So, the suspensory ligaments. They're attached to the ciliary muscle. These are used to form the ciliary body, which secretes aqueous humor. Okay? So, aqueous humor, which we said was earlier used for nutrients and supplying to the cells of the eye, in addition for the shape. Okay. So the posterior chamber is that space area behind the iris in the back of the lens, filled with aqueous humor. Is it meant to be aqueous humor? Because we said before in the anterior that has aqueous humor. Okay. But it's also filled with, so it helps with shape as well. Okay. The vitreous chamber is filled with vitreous humor, a jelly-like substance for pressure to the eye to give nutrients inside the eye. Okay, I do need to review that. I do know what the retina is. The retina is the region in the eye that has photoreceptors where rays of light can be converted into electrochemical impulse that travels through the occipital pathway. Okay. The macula is the region that's rich with cones, but there's also rods. The fovea, we'll think about it like this. Fovea reminds me of funnel, which means it's completely covered in cones. So this is the region for color sight. Cones, they detect color and discern high level of details what you're observing. Cone shaped. Well, no shit. Huh. Rods, they just detect light or dark. And can be regulated in upregulation or downregulation of the eye based on the sensitivity that it needs to adapt to. Choroid is the pigment black in humans. So it's the pigmented black in humans, which is the network of blood vessels that help nourish the retina. Okay. It's black. It's black. It's black. All light is absorbed. Huh. It doesn't really make sense. But okay. It helps absorb light. I'm assuming that's what I'm going to interpret as saying. Alright. The sclera is that white part of the eye, and it's used as where it connects to muscles in the eye. Sorry, it connects muscles in the face to the eye, so you can move your eye around. So there's just a diagram of what's going on. Sclera, choroid, conjunctiva is the part connected to the eyelid. Cornea, anterior chamber, aqueous. Where's the posterior chamber? Right here. Alright. So let's continue with visual sensory information. So visual sensory information is transmission is the electrical activation of one neuron by another neuron. Perception is the conscious sensory experience of neural processing, which makes sense. Processing is the neural transformation of multiple neural signals into perception. Transduction occurs whenever energy is transferred from one form to another in this case. So transduction example is the light energy could be converted into chemical energy in the... Oh, they use that one. Sensation requires a physical stimuli to be converted into a neural impulse. So someone poking you could be a sensation. In the case of the eye, light is being converted into a neural impulse by a photoreceptor. What is light? That is truly a hard question right there. But Light is an electromagnetic wave which flows generally from our sun that contains gamma rays, which are low waves, and AM and FM waves. Visible light is in the middle of the spectrum. Violet is 400 nanometers, red is 700 nanometers. Highest to lowest wavelengths, red, orange, yellow, green, blue, violet. Red's long. So, how does light promote perception? So light enters the pupil and goes through the retina, which contains rods and cones. There's more rods compared to cones because we needed them more evolutionary for night vision for hunting or prevent being predation of us. So when light comes in, it goes through the pupil and hits rods. Normal rods is turned on, but when light hits it, it turns off. When rod is off, it turns on a bipolar cell. It turns a retinal ganglion cell, which goes to the optic nerve. So when light hits the eye, it turns it off because we don't want to see it anymore. Let's think of it that way. Light enters the eye, hits a rod, it turns it off, so it promotes the next cell to be turned on. Because you have to flip the switch to turn on the next cell. There we go. That makes sense. The three types of cones that we can see is red, green, and blue. Almost all are centered in the fovea, which is the center of the macula. Helps us find where's Waldo. The phototransduction cascade. So the phototransduction is light enters through the eye, through the cornea, through the lens, hits a router cone, which turns the router cone off, which promotes the bipolar cell that be turned on, which turns on the retinal ganglion cell, which goes to the optic nerve and then the brain. The phototransduction is the process of the rod turning from on to off. So when you're sleeping, those rods are on. That makes sense. So bipolar cells. Bipolar cells are found in the retina. These cells send visual signals from the rods and cones to ganglion cells. Ganglion are body cells outside of the central nervous system. So that makes sense. So the bipolar cells is basically receiving the information from the rod and sending it to the ganglion cells to be sent to the optic nerve. The ganglion cells are found in the retina. Gang of lions standing on top of polar bears. Alright. Okay. Sure. So, the optic nerve. The optic nerve visually signals after having been picked up by rods and cones and transferred from the bipolar to the ganglion cells. It leaves the eye through the optic nerve, which is really just an axon of the ganglion cells. So the optic nerve is just axons of the ganglion cells. And axons make their way out of the back of the eye into the brain. Okay. So, we have two theories that we want to talk about with sight. Okay? The trichromatic theory of color vision. I need to review these theories better. That's okay. This theory talks about that we have cones that are receptive to three colors, red, green, and blue. These three colors are mixed together to perceive color. The only problem with this theory is that while our eyes can mix together, say red, yellow, and make orange, we can't seem to mix red and green or blue and yellow. To explain this, we have another theory. So the trichromatic theory is less accurate because we can't mix these multiple colors together. So the opponent process theory of color vision. Okay, let's read it. Oh shit. Why is it highlighting like that? But fuck it. Sure. There you go. Good enough. This theory states that you have cones that perceive four colors, red, green, blue, and yellow. And that the red and green cones oppose each other as the blue and yellow. So black and white sensitive cones are also opponents. Between these opponents, only one color can dominate at a time. So, let's look at these figures because I'm kind of confused on this a little bit. The trichromatic theory says that we have three types of cones, red, green, and blue. They combine to make all colors that we see. Okay, that makes sense. Mnemonic, picture tricycles with red, green, and blue being mixed together in a blender. Okay, that's the theory that I always knew. But let's look at the opponent process theory. The theory that there are four colors in pair, red versus green, blue versus yellow, black versus white. Only one color in each pair can be seen by your eye at a time. Mnemonic, picture that the colors are opponents in a boxing ring. Okay, sure. Makes sense. Kinda. Back to the phototransduction cascade. We kinda already talked about this, but I'm guessing this is going into further detail. So the phototransduction cascade makes the brain recognize that there's light entering the eyeball. The process of making the light neural impulse by turning off the rod. We already talked about this. Retina is made of a bunch of different rods. Yep. We already talked about this. Yep. Turns it off. The phototransduction is a set of steps that turn it off. Okay. Here's what we need to read. Inside the rod are a lot of optic discs stacked on top of one another. A lot of proteins on the disc. One is rhodopsin and photodopsin, which contain a single molecule of retinol. When light comes through the pupil and hits the retinal, then its rod, some of the light hits rhodopsin, cause the retinal to change conformation to bend in shape. Okay? So basically, when light enters, it causes a conformation change in retinol, which allows us to change shape to begin this cascade. There's a molecule transduction, alpha, beta, and they're attached to rhodopsin. Okay? When the rhodopsin changes shape, transducin breaks from rhodopsin and alpha subunit to another called photodiesterase, which cleaves phosphate groups, phosphate ester groups. GMP and converts to the GMP. That makes sense. If you take in biochemistry, that does at least. Lots of sodium channels on the rods allow for sodium to come in. You want sodium to come in to turn it off, to hyperpolarize the cell. Okay. When the channel becomes unbound, it's hyperpolarization and yep, I was right. I just knew that from my neuroscience class. The rod turns off. On and on. We already talked about that. When dark, rods turn on. So like I was saying, when you're sleeping, the rods are turned on. On center, bipolar inactive. When off center, bipolar is turned on. So just talking about the opposite. Okay. So phototopic vision occurs at levels of high light. Okay. So let's think. Phototopic means photos have a high flash, so they have to have high light levels. Mesotopic occurs at dawn or dusk, involves both. Okay. Meso means middle, so think about middle lighting. And scotopic is very low light. How would I remember that one? Scotopic is very low light, so let's think slow depolarization of, or hyperpolarization of that rod. Okay. Photoreceptor rods and cones. They're going very in depth in this content right now. But let's keep going. I'm just going to keep drinking my water bottle away. A photoreceptor is a specialized nerve that can take light and convert it into a neural impulse. Okay. Inside the rods are optic discs, which are large membranes. We already talked about this. Difference between rods and cones. There's more rods than cones, yes. We knew this because we were first evolved to have more light and dark vision for hunting and prevent predation. Rods are more sensitive to light, which makes sense because they only focus on light and dark, while cones are different colors. I don't know why they say primarily are 60, 30, and 10. They also said there's a yellow receptor. It contradicts itself, but I don't know. In the previous theory of the opposing theory of light, rods have a slow recovery time, cones have a fast. That makes sense. Because rods depend on, there's light every second of the day, so they have a slow recovery time. Cones have a fast, so you can have a different change of color when you turn your head. Photoreception distribution in the retina. Okay. Where optic nerve connects to the retina, the blind spot is where there's no cones or rods. So when the optic nerve enters the retina, there's a blind spot. Rods are found more peripherally, cones are found primarily in the fovea. The fovea is the dimple in the retina. There's no axons in the way of light, so it gets higher resolution. At the peripheral, light has to go through a bundle of axons and some energy is less, so the fovea light hits cones directly. Less light gets to the rods. That makes sense, because we want to have the most light to enter the eye in the middle, because we want to determine its color. Well, generic background light is fine. Okay. Okay. I'm starting to get burnt out of visual field processing, but we'll keep going. We'll keep pushing on. So, how our brains make sense of what we're looking at. The right side of the brain is controlled by our left. So the right vision is also on the left side of the brain. Wait a second. I may have said that backwards. All right visual fields go to the left side of the brain. All left visual go to the right. That makes sense. Because they cross in the chiasma, where on the left side, it will go to the right side of the eye, and it'll be on the right side of the eye. So, rays of light from the left visual field hit the nasal side of the left eye and hit the temporal side of the right eye. Vice versa for light from the right visual field. Ray of light from the right visual field hits the nasal side of the right eye. Okay? So, optic nerves from each eye networks the electrical signal to the brain, converges from each eye into the optic chiasma, and then breaks off and digs deep into the brain. Now, all light from the nasal side of the both eyes cross from the other side, so left nasal info goes to the right side and vice versa. On the other hand, all axes leading to the temporal side do not cross to the optic chiasm. What it effectively does is the right visual field goes to the left brain and the left visual field goes to the right side of the brain. That makes sense. So, right, the right side. So this is the left side. Goes to the right eye. This will be the last section till before I take a break, because we've been going at it pretty hard for the last hour and a half, and I feel myself starting to burn out of just going through it. So I'll take like a 5-minute break after I get through this one passage section. Feature detection and parallel processing. So feature detection is what we talked about earlier with binocular perception, binocular cues, and monocular cues. So feature detection is when we're looking at an object, you need to break it down into component features that make sense of what you're looking at. There are 3 things to consider when looking at any object: color, form, motion. So let's start with color. Color, according to the trichromatic theory, there's 3 types of cones: red, green, and blue. Remember, red objects reflect red, green objects reflect green, and blue objects reflect blue. Physics. Objects reflect red, red light hits red cone. That makes sense. So we have that, and then we have form. We need to figure out the boundaries of an object and shape of the object. The paracellular pathway, good at a spatial resolution, but poor temporal. The paracellular pathway is good at spatial resolution, boundaries and shapes, and color, but poor temporal for motion. So that's why we have issues with determining the form of an object when it's in motion. So motion is the magnocellular pathway. Has a high temporal resolution and encodes for motion, but has poor spatial resolution. So rods are responsible. Acronym. Motion equals magnocellular pathway. M and M. Okay. So parallel processing is just multiple of these different perceptions, cues, being incorporated into one and focusing it all at the same time. So this is where I'll take my break through the first part of this information. So I will return after a short break.